We are welcome to Journey on Multivariate Calculus, another multiple integrals. So far we've done the applications of the double integrals in certain aspects. So the first aspect we looked at was the extrema, and then we had the linear approximation, directional derivative. And today we are taking another interesting application on the surface area. I believe surface area should ring a bell, but let's look at a motivation to that. Now let's think of these things as I have on my slide here. If you're asked to wrap a gift of any shape at all, whether it's a square, a rectangle, it's a circle, a prism, any form of shape, you should be able to wrap that gift, a hamper, anything. If you're asked to paint a room, what do you think comes to mind? If you're asked to lay a carpet in a room, what should you do and what comes to mind? And what can be the best measurement you can have for the carpet size? If you're asked to label a can, what do you need to do? You realize that in all these aspects of what we are thinking of, the best question we are asking ourselves is, how much materials do we need? How much yards of wrapper do you need for the gift? How much containers of paint do you need for the room? So you realize it depends on the shape of the room or the sizes of the room given. How much yards of carpet do you need to lay? It depends on where you want to lay the carpet. Is it the center of the room? Is it the entire room? How do you want to label the can? Is it the entire can or just some part of the can? And so this is the questions we ask ourselves when we are dealing with surface area. So how much materials do I need to do all these things? I need to know the object surface area, and that'll give me a fair idea of the right measurement I need to complete the task. And so there's a simple motivation to surface area. Now the next question is, how do we measure this, or the units given to surface area? It is always a square unit. So centimeter square, meter square, inches square, feet square, any form of unit you have, it is the squares of that unit. And that is a simple motivation to surface area. Now let's go to the technicalities of this. The next question is, what is a surface area? So I want you to go back and think of the images we used. I want to change the pen to green. Think of the images we use here. The gift, the room, the carpet, the can. If I want to find a surface area of it, I need to know the total area. So the surface automatically becomes the total area of the object. But we're not doing any other object at all. You realize that these images I was talking about, or these paintings and stuff, they will come in the form of 3D objects. So that is the focus of surface area. 3D objects. Okay. Now what are some of the 3D objects we can think of? So it can be a cube, it can be a rectangular prism, it can be a sphere, it can be a cylinder, it can be a cone. These are three-dimensional objects. For two-dimensional objects, we have circle, we have the square, we have the rectangle, we have the triangle. Those are the 2D parameters. If I want to find the surface area of this, right from basic elementary schools, if I want to find the surface area of a cube, I need to know the number of sides. So I think this has 6 sides, 6 equal sides. So if one side is a square, I have to add this one 6 times. So I just have to multiply by 6. This gives me the surface area of a cube. If I want the surface area of a rectangle, I know 2 sides are equal and another 2 sides are equal, and you have to add those 2 sides together. So you need to find the area of one part and then add it up. That gives the total area. If I want a cylinder, we know cylinder, if I have to share this, there's one circle up, one circle down, and then there's a rectangle for this part. The height part is a rectangle. If I know the area for a circle, so I have area 1, area 2, and then area 3. When I add it up, I can find the surface area of the cylinder. In the same way, if I have a cone, I know cone is made up of a triangle and then a circle. So I find the area of a triangle, area of a circle, and I add these two. I should be able to find the surface area of the cone. This means that if you have a complicated three-dimensional object, you have to demarcate it and then find the pieces together to get a total area. Now, most of the things you'll come across is to finding the length, the width, the height, the radius, because we have sphere and circles, and then the slant height, like the cone. The cone is not a straight height like the cylinder, it is slanted, and these are the things you must look out for. But we don't worry ourselves with all this form of measurement. We want to use the double integrals, and that is the interesting aspect of finding surface area by using the double integrals. So let's see how we are going to do that here. First, you need to know the surface in which you are dealing in. How does it look like? And then also you need to know the region in which your surface lies in. Is it in the XY plane, YZ plane, XZ plane? Where is your region of focus? And then when you know these two, you can simply use a formula that will give you, there's a general formula for finding surface area. So it's given by equation 1, a double integral over the region R, the square root of some partial derivatives dA. Now that is where now partial derivative comes in, because you have f of x squared and f of y squared. By this formula, I can find any total surface area of any 3D object, as simple as that. But there's a caution here. The caution says not just because you've seen the formula, so you're going to just do a substitution. No, there are key things you must look out for, and that key thing is finding the region of your surface. It's very, very important. Do not just say I have a formula, voila, so I'm going to do a substitution. No, always find your R. You realize that when you find your R, it will determine the nature of your dA, as we've done so far. Okay, so with that said, let's take some examples. I'll be quick with these examples. I'm not going to compute the entire double integrals. I'm just going to show you how to do the substitutions. So example 1, it says determine the surface area of a plane over a rectangular region. So there are key things I would always want to look out for to make my life easier. First, I would like to know my surface is given by this function. I want to know my region R, that's the focus. From the question, it's a rectangle as I have here. If it's a rectangle, then I know what I need. I need my rectangular or Cartesian domain. Okay, so I need to find my x limit. From the question, x limit is given. I think the green pen is not doing justice. Okay, and then my y limit is given as 0 to 2. So x is 0 to 3, y is 0 to 2. I'm sure you know how to get this stuff. Then I need to do some partial derivatives. If I want to find f of x respect to, this is the same as finding z respect to x. Okay, and that's giving me 1. F respect to y will give us 2. That is from z. Okay, now we can do the substitution now, and it's going to be 1 square plus 2 square plus 1. This one is always constant in the formula. I hope you don't forget that. And then look at my dA. Because it's in the Cartesian coordinate, I can have it as dx dy, you know that, or dy dx. If it's dy dx, I still have 1 square plus 2 square plus my 1. But then what we have to take care is the limit of the integrals. If I'm having dx dy, x is my inner integral, so I have 0 to, I have 0 to 3 here and 0 to 2 here, and that is it. If it's dy dx, I have 0 to 3 here, 0 to 2 and 0 to 3 here. As simple as that. And either way you evaluate this, you must get the same answer. So I know I'm going to have some double integral and then the square root of 6, if I'm not wrong. Yeah, either the x dy or dy dx. And whenever you compute this, my answer says you should expect to have 6 root 6 units squared. So I told you initially, it's not about solving the problem, it's about knowing how to get through it. Okay, and so you can compute this and then verify the answer. Let's take example 2. Example 2 again, there are things I'm going to look out for. What is my surface given? My surface is square root of 4 minus x squared. What is my region? It's a rectangle. Don't forget, it's a rectangular prism. Let me just write it. If it's a rectangle, then I know I'm looking at the Cartesian coordinate, a rectangular domain. Yeah. So I need to know my x range. It is given, as simple as that. It is already given in the question. Alright, so I need to find my partial derivatives. I'll leave this one out for you to figure it out. But I know z of y is 0 because there's no term of y in there. You want to find what this guy is. This is the same as 4 minus s squared to the power half. And by, you know what to do with this derivative, so I'll leave that up to you. My focus is on, so I know I need to find some f squared, some y squared is 0 plus 1. Okay, either dx dy or dy dx. If it's dx dy, you know it means the inner limit is my x coordinate 0 to 1, my outer limit is 0 to 4. Okay, if it's the other way around, dy dx, then you know I have 0 to 4 here, 0 to 1 here. And whatever you get, you must do the calculations for me. If you want to pause the slide and check the answers, you are good to go. If I do this integral, it says f of x is 2 over, it's negative x over square root of 4 minus x squared. You want to check this derivative out, it's correct. Plus 1 here. And when you do that, you are supposed to get 4 pi on 3. We've already gone through double integrals. That is why I'm not computing the double integrals for you. The third example. Now you ask yourself, what is the surface here? The surface here is given as y squared plus 4x. Yeah. What is the region here? I told you that we always must find the region. The region here is a triangle. It means we are no more in a rectangular domain. Something has changed. Triangle gives us the general regions, if you've forgotten, or the non-rectangular domain. It means we can't do the approach we did in the first two examples. We must do something else. And you know, in general domains, you must first draw out your region and then do some slicing through the y-axis slice, y slice, or you must do the x slice. If I draw my domain with the vertices given, this is what I'm supposed to get. This whole part of the work. You want to try it out. If you forgot, you can go through the general region video and then see how to do the slicing. So in this case, if I'm slicing through the y-axis, I know y, you must find the equation of the lines. This is y equal to x, this is y equal to 2, x equal to 0. So it means that I'm going to have 0 to 2, and then y is going to be x to 2 if I'm tracing the lines out. Over here in the x direction, x will move from 0, this is y equal to x still, this is y equal to 2 here. Yeah, so it means that I have 0 to 2 for my y part, and then my x part will be 0 to y. Yeah, this is my coordinates. So either way you want to choose it, you are good to go. So let's find the partial derivatives. So this will go with this coordinate, this will also go with that coordinate. Okay, partial derivatives for here, I'm supposed to get 4 for this, and then 2y. Don't forget the function already given. Okay, now let's do the substitution. Double integrals for the surface area. I know I'm going to get some 4 square plus 2y all square plus my 1. because the square root of f of x squared plus f of y squared plus 1. Okay, my interest here is which ones are you using. If it's the x dy, you know the rules of the game. Your inner are variables, your outer are constants. So realize that this is the x slice part and this is the y slice part. I hope that is not cumbersome to view. So let's just add our coordinates. In the xy slice, we will have 0 to y here and 0 to 2. The outer limit must be constant, and then the inner limit are variables of the outer integral. If I'm sliding through the y-axis, I know my limit was, let me scroll up and check it again, 0 to 2 here. I hope I'm not doing something, and then x to 2. Okay, so this will be my whatever limits of integrals I must add, and then my integrand sorry, becomes 16 squared plus 4y squared plus 1. That's the same as having some double integral of square root of 17. No, 16 squared is not 17. I mean, you should know what to get. Okay, so yeah, so that's 17 plus 4y squared, because 4 squared is 16. Either dx dy or dy dx. I've already done the coordinate for you. If you solve this double integral, you must get 9.955. So pause the video, check the slides, and then compute the double integral. And that's how simple surface integrals are done. The last example here, again, I need to determine my surface. It's given by 9 plus x squared plus y squared, and this is the same as the function f of xy because it's in terms of 2. What is my domain? It says it's a disc. Disc is a circle. Disc is a circle. So the first two examples, we did rectangular coordinates, we did the general regions, and now we're on a circle. What comes to mind? Polar coordinates. Polar coordinates. We said that if you have a circle, it's easier evaluating your domain in the polar coordinates. It means we need some r and theta. How do we find theta? Because it's a circle, we know theta will range from 0 to 2 pi. But what about my radius? Starting from the center to any point of the circle. But it says that your r is given as 0 less or equal to x squared plus y squared less or equal to 4. By the convention of rectangular to polar, I know there's the same as 0 less or equal to r squared less or equal to 4. This means that I have 0 between r and then 2 from here. If I find the square root of both sides, that is my radius. So 0 to 2. Now I can find my partial derivatives from the, I have 2x and I have 2y. Please, you can either find a partial derivative in terms of r and theta, but I want to move it gradually from the Cartesian, okay? So first do with x and y as we already know in our formula. Then we can do the substitution. 2x squared plus 2y squared plus 1 over my region r. But I don't have limits for x and y. Mind the a. If it's polar, becomes r dr d theta. And so let's expand the integrand here. I know if I'm taking the r as the inner integral, it means I have 0 to 2 here and then 0 to 2 pi, because theta is my outer integral. This becomes 4x squared plus 4y squared plus 1. You realize that you've moved from the rectangular domain to polar, but you still have x and y, so it means you must do something else to the integrand. If I factorize 4 out, I'm going to get x squared plus y squared plus 1 r d theta, 0 to 2, 0 to 2 pi. Then I can now reshape this or modify this to my 4r square plus 1 r d theta. Where did I get this? This is the same as r square from the convention, and that is my surface area. You compute this integral and you're supposed to get what's it, my answer. That's it for you. So take your time and know when to use Cartesian or rectangular domain, know when to use general regions, know when to use a polar coordinate. It all depends on the region of focus. And that brings me to the end of my analysis here. For example, 5 and 6, let's just figure these things out. The surface is given as xy. That's a function of xy. There's a surface, but it says it lies in a cylinder. The region is a cylinder given as that. It means that I'm looking at the region here in the cylinder. So that region is a disc or is a circle. So you know automatically we are going to use polar coordinate. How do we do that? You want to pause the video and check the slides out. Then example 6 also, it says that your region lies above the closed disc. It is simply given as this. So you know you're going to use polar. This is the same as r squared less or equal to 9. R is less or equal to 3. It means r ranges from 0 to 3. And because it says closed disc, my theta is 0 to 2 pi. As simple as that. You must check the integrand. It must move from 25 minus s squared minus y squared to something else. Okay? And that is what you have to do. So that is it for how to use the polar coordinates, or sorry, the double integrals for finding surface area. And after that, we'll take the last thing under integration, that is triple integrals. Thank you very much.